Our topic for this video is inertial frame of reference. So before we start, did you know the fact that everything is moving? When we said that a car is moving 100 km per hour on the freeway, we are ignoring the fact the surface of the earth is rotating around the center at about 1700 km per hour at the equator, and earth is also moving around the sun at 30 kilometers per second, and the entire solar system move around the galactic center at 20 kilometers per second, and the Milky Way galaxy is moving through the universe at about 230 kilometers per second. We don't notice the movement of the earth, the sun, and the galaxy in our everyday lives. To us, the earth seems to sit still. Inertial frame of reference. This is an object, a person or location that we pretend that is completely still, and we assess the motion of other objects relative to this inertial reference frame. For example, if we treat the Earth as an inertial frame of reference, and we ignore its rotation and movement through space, it becomes so meaningful to say that this car is moving directly at north in 100 km per hour relative to the ground. But if we are inside the car moving with constant velocity, it seems as though we are not moving, but rather the surroundings are rushing past us at 100 km per hour. The car has become the inertial reference frame that is standing still and everything is in motion around us. I know it's hard for us to say that the car is not moving, but remember, it is just as incorrect to pretend that the earth isn't moving. So it is all relative. I will show you another example of an inertial reference frame.
Imagine you are sitting in a moving train. You toss a ball into the air and catch it. To you, the ball went straight up and down. But to an observer on the ground, the ball followed a parabolic path as the train went past. This is because when the ball leaves your hand, it still has all of the forward velocity that the train does. But if you are inside the inertial reference frame of the train is not moving at all. It is the surroundings that are moving. So the ball no longer has any horizontal velocity, only the vertical velocity you impart to it by moving your arm to throw the ball. Assigning frames of reference and understanding what they mean for the motion of objects is a big part of physics. And although some aspects of this kind of thinking seem obvious, they were not always well understood. Galileo was the first to rigorously describe relative motion after doing experiments in a moving ship. He found that if he dropped a ball while the ship was moving with constant velocity, it fell straight down, just like it did when the ship was stationary in the port. He then contemplated how a fish nearby would view the motion, with the ball moving forward as it falls, and how this differs from his own experience. He used these experiments to prove that velocity measurements depend on which reference frame you adopt, and he published his findings in a book called Dialogues Concerning the Two Chief World Systems in 1632. These ideas were extended to describe the motion of the Earth around the Sun instead of the other way around, by proving that the Earth could be moving even if we don't feel it. This got Galileo and other scientists into hot water with the Catholic Church. But humanity eventually caught up to his revolutionary thinking. We refer to this portion of his work as Galilean relativity, and these concepts will be built upon to enter very strange territory when we cover Einstein's special relativity in the modern physics course. But for right now, we won't go flying through space. We have much more work to do on Earth, which, despite its rotation and motion, is actually quite a good approximation of an inertial reference frame, one that will be used frequently throughout our study of physics. With each topic we go through, whenever we examine an object's velocity, just remember, it's all relative.